the next objective is to actually perform a significance test about a population proportion. So the first objectives we looked at different parts of a significance test. But now when we are asked to run or conduct or perform a significance test, we use the state plan do conclude process. So the state is going to be our hypotheses, and we're defining the parameters of whatever it is that we're testing about. Plan, we have to check the conditions. And we also need to state our method of inference. So for instance, we've learned how to do a t interval, a z interval, and now we know how to do a one sample z test for a proportion. In the do section, we're going to perform the actual calculations. So we'll compute the test statistic, and then we'll find the p-value in that order. And then finally, we'll make a decision, which means we will reject or fail to reject the null. So again, this is called a one sample z-test for a proportion, where we have our null hypothesis, some parameters equal to some value. And you've seen this formula before. This is the standardized test statistic. It is a z-test, so we have a z-test statistic. So in this case, our hypotheses, the alternative could be that it's greater than, or it's less than, or it's not equal to. And we've discussed before that if it's greater than or less than, then it's called a one-sided test. If it's not equal to, then it's a two-sided test. And so basically, if we're doing a one-sided test, we're finding the probability of it being greater than some value, greater than. If it's a one-sided test and we have the alternative is less than some value, we're finding the probability of it being less than some value. Not equal to, we have to find the probability of it being greater than or less than. So the three conditions are important because the random condition has to ensure that our p-hat is trustworthy. The large counts condition has to ensure that the sampling distribution of p-hat is approximately normal, which allows us to assume the z distribution is true for this distribution. The 10% condition allows us to find and trust that the standard deviation of the sampling distribution, according to the null, is true. So it's the same three conditions, but this is where they tie into the importance of a z-test. The important thing we have to remember is that we're always assuming that the null is true when we're conducting a significance test. Let's take a look at our first example of how to do a significance test, and this should be a familiar problem for you. A potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer finds convincing evidence that more than 8% of the potatoes in a shipment have blemishes, the truck will be sent away to get another load from the supplier. A supervisor selects a random sample of 500 potatoes from the truck. An inspection reveals that 47 of the potatoes have blemishes. Carry out a significance test at an alpha level or a significance level of 5%. What should the producer conclude? So the first step in this is to state our hypotheses and state what the parameter is that we're running a test about. We've stated our hypotheses where we are running a test about the true proportion of potatoes in this shipment that have blemishes. And we want to assume that the null is true until proven that it's not. And we're only worried our alternative is greater than 8% because we don't care if it has less than 8%. If it has less than 8%, then they won't send the shipment back. It only matters if they have more than 8%. So that's why our alternative is greater than 8% here. So just so we're on the same page, they're taking a sample of 500 potatoes from the shipment and trying to use that sample to determine if the whole shipment has higher than an 8% proportion of blemished potatoes. So in the state, we list our hypotheses and what the parameter is. And now in the plan section, we'll name our method of inference and we'll check the three conditions so we can proceed with the test. This is a one sample z-test because it is about a population proportion. Just like the intervals, if we do an interval about proportions, it's a z. If we do an interval or a test about means, then most likely it will be a t. So we'll learn that in the next section. They told us it was a random sample of the 500 potatoes from the shipment, so the random condition is met. It's reasonable to assume that 500 is less than 10% of all the potatoes in the shipment, so the 10% condition is met, which means we can trust the standard deviation of the sampling distribution. You could also say it's reasonable to assume there are more than 5,000 potatoes in the truck shipment. The large counts condition is met because the expected successes and failures are both greater than 10. But we must remember that here in the sample, we had 47 blemished potatoes. But we're not using the sample, we're assuming that the null is true. So we have to use the null as P here. So that's why it's multiplied by 8%, not using just the 47. So that's where we get the 40 and 460, but it is met, which means sampling distribution of P at is approximately normal, assuming that the null is true. And so now we can move to the do part where we'll actually write out our sample statistic, and we will find the test statistic and the p-value. Our sample statistic, 47 out of 500, is 9.4%. Now we'll use this to calculate the standardized test statistic. So we use our statistic minus the null divided by the standard deviation of the statistic, assuming that the null is true, and we get a standardized test statistic of 1.15. So it's 1.15 standard deviations above the mean. And now we'll use this value to calculate the probability of that sample occurring, or the p-value of this test. So you don't have to draw the picture like this, but I just want you to see this is a one-sided test because our alternative is greater than. So I'm trying to find the probability of a test statistic of 1.15 or more extreme. So that's why it's a one tail, it's just the upper tail. And so I can use my calculator, normal CDF, to calculate the probability of this z-score occurring by chance alone. And we get a p-value of 0.1251. So remember, in 9.1, we learned how to interpret a p-value. And what this means in the context here is if there really is 8% blemished potatoes in this truck, if the null is true, then there is a 12.5% chance that we take a random sample of 500 potatoes and we get 47 out of 500 with blemishes, which means it's relatively likely 12.5% occurs. It's not extremely unusual, which is why in the next step of this problem, we're going to make our conclusion and we are going to fail to reject the null, because if it is 8%, if the truck really has 8% blemished potatoes, it's not that unusual to get the sample that we got in our statistic or in our example. In our conclusion, we have to be specific, and because our p-value of 0.1251 is greater than alpha of 0.05, we fail to reject. There is not convincing evidence that the true proportion of blemished potatoes in the shipment is greater than 0.08. So we have to make sure we show our p-value is greater than alpha. We need to say that we failed to reject, and then we need to say that there is not convincing evidence that the null is true. Now, if you fail to reject, then we can't say anything that makes it seem like we believe the null is true, because we're not proving that the null is true. We just don't have evidence to say it's false. So saying anything that we believe it's true will lead to a loss of credit. For example, if we say something like there is convincing evidence that the true proportion of blemished potatoes is 0.08, then we won't get full credit, because the only time we have convincing evidence is when it's against the null. So we either have convincing evidence or we don't have convincing evidence. And when we don't have convincing evidence, then we fail to reject the null. The last example was a one-sided test, and I want to talk about a two-sided test here. With a two-sided test, you're going to see in a moment that really all we have to do is conduct it like a one-sided test and then multiply the p-value by 2 because it's going to include both tails instead of just the upper or the lower tail. But we'll run through this example just so you can have an experience with one anyways. According to the Centers for Disease Control and Prevention website, 68% of high school students have never smoked a cigarette. Yan Hong wonders whether this national result holds true to her larger urban high school. For her AP Statistics class project, Yan Hong surveys a simple random sample of 150 students from her school. She gets responses from all 150 students, and 90 say they have never smoked a cigarette. Is there convincing evidence that the CDC's claim does not hold true at Yan Hong's school? So first we'll state and set up our hypotheses. Our hypotheses, we assume that the proportion at our school is equal to the national claim. So we say that the proportion of all students at Yan Hong School who would say they never smoked a cigarette is equal to 0.68. The alternative is that we don't know if we think it's higher or lower. We just don't know if it's different. So if it's different, it's just not equal to, and that makes this a two-sided test. And we've stated our alpha level or significance level is going to be 5%. So next we'll state that this again is a one sample z-test, and we'll check the 3 conditions as well. The random condition is met because she took a simple random sample of 150 students. The 10% condition is met because it's safe to assume that 150 students is less than 10% of all students at a large urban high school. And the large counts condition is met because the expected number of successes would be 102 and failures would be 48, which are both greater than 10. Now you have to remember, you're assuming the null is true here. You're not using the sample that she actually took. So now we can do the test and actually calculate the 2 things, test statistic and the p-value, before we make our conclusion. So our sample statistic is 90 out of 150, which is 60%. So we find our standardized test statistic, which is the p hat minus the null divided by, oops, this is an error. This should be the null is true, not the sample. This is a mistake that I see a lot of students make where they plug in the sample statistic, but it needs to be assuming that the null is true. So I'll change this to 0.68. There we go. I've changed it to 0.68 and 0.32. And so if you punch all this in the calculator, it'll give you a test statistic of negative 2.10. And we'll use that to find the p-value. So here's a picture of why it's called a two-sided test. You found the test statistic, but since it's not equal to, we're looking for it being less than this value or this value or greater. So that's why it's the 2 sides of the tails here. And so we're going to find the probability of it being less than, and then we're going to multiply by 2 because this value or this probability is the same above. So the area here from negative infinity to negative 2.1 would be this side of the tail to get 0.01785. Now we need to multiply by 2 to get this value and include both tails for the two-sided test. And now we have our p-value of 0.0357, and we'll use this to make our conclusion and compare it to our alpha level of 0.05, which you can see this value is smaller, which means we're going to reject the null hypothesis. And I'll write that out in context here. Because our p-value of 0.0357 is less than our alpha level, we reject the null. We have convincing evidence that the proportion of all students at Yan Hong School who would say they never smoked a cigarette differs from the CDC's claim of 0.68. So again, make sure you're measuring the p-value against alpha, say that we reject, and then this time we do have convincing evidence. And whenever we have convincing evidence, it means we're rejecting the null. If we don't have convincing evidence, then we fail to reject the null.